Howdy guys, in this video we're going to preview recursion and recurrence relations. So let's jump right into it. Alright, so here's a basic introduction of recursion. So recursion is the process in which a function calls itself either directly or indirectly. Recursion formalizes the process of recognizing how solutions to smaller cases of a problem can layer by layer be built up to solve any case of a problem, no matter how enormous. So basically what we do is we try to solve like smaller bits of the problem and then we build up based on that to ultimately solve the bigger problem. Alright, so let's try to understand when do we use recursion. So recursion should be applied as a technique when the problem you're solving is like an onion. Using recursion requires realizing that a big, complex problem that's likely to make you cry is really just a slightly smaller problem plus one super thin layer, and that problem in turn is just a slightly smaller problem plus one super thin layer, and so on. So recursion can do anything that loops can do, but it can also do much more than that. One thing to note over here is that recursion is often slower than loops and has a maximum depth limit, which means that there's a limited number of iterations you can do with recursion. And we'll discuss the reason for this on the next slide. Alright, so basically whenever a function has been called, the information of the calling function is stored in a runtime stack. So runtime stack is basically, it's also called a recursion stack sometimes. It's basically a stack which contains information about the function, which is like basically calling some other function. So if you're doing recursion, then the parent function kind of is stored in the stack, and then whenever the child function finishes its execution, so basically after the function has completed its execution, the stack contains the information about the calling function or like the parent function, and then the return value of the child function, um, if there's any, is returned to the calling function and the program continues execution. So that's basically how the recursion works. And so that's also a reason why recursion has like a maximum limit of iterations, because the stack has a limited amount of like memory allocation basically. So if you run out of memory, then you can't like keep calling recursion again or keep using recursion. Alright, so a recursive function is basically consisting of two things. The first one is the base case, which is basically the stopping condition. That's the condition where the recursive function stops calling itself again and then basically gives you, it's like the smallest problem for the recursive function. And then there's the recursive case, which basically results in another recursive call to like solve a smaller problem and then ultimately solve the bigger problem. So we have been given an example over here. We are basically trying to make a recursive function to find the factorial of any integer n. So basically the way this function works is that if n is equal to 0, then we just return 1. But if it's not 0, or if it's like basically greater than 0, then we'll return the product of n and factorial of n minus 1. And so in this case, if n equals to 0, return 1 is basically the base case, because that's the case where our recursive function stops calling itself again. Whereas the second statement, which is else return the product of n and factorial n minus 1, is the recursive case over here. Alright, so let's look into some different types of recursion. So one of the important types of recursion is called tail recursion. And so tail recursion is nothing but basically a recursion where you have just one recursion call, and when the call is made at the end, so like it's at the tail basically, and so there's no other statement left to be executed after that. So for example, we are trying to make a function, a recursive function, which can basically print the numbers from an integer n to 1 in decreasing order. So what this function basically does is that if n is greater than 0, then we'll print that number, and then we'll print a space, and then we'll again call the same function again with an argument of n minus 1. So it basically breaks down to a smaller problem. And then it keeps doing that until n is equal to 0, in which case it will basically print an end-line character, and that's basically the base case. And so as you can see from this example, this function is an example of tail recursion, because the descending order, like the recursion call, basically is made at the end of the, or towards the tail of the function. So once you do recursion, you basically break out of this loop. And yeah, I think there's a typo over here. This should be a braces on, like a closing braces basically. Alright, so here's another example, another type of recursion. So this is called binary recursion. Binary recursion is basically characterized by two recursions for every non-base case. I think it's easier when we look at an example. So here's a quick example for that. So basically this is a recursive function which finds the nth Fibonacci number. And so what this function does is that if n is less than or equal to 1, then it will just return 1. Else it will return the Fibonacci number, the n minus 1th Fibonacci number plus the n minus 2th Fibonacci number. And so as you can see, there's two recursion calls here for every non-base case. So this is the base case and this is the recursive case, and we are basically calling using recursion 2 times in the recursive case. So that's how this is binary recursion. Alright, and there's some other types of recursion which are basically important or good to know basically. One of them is indirect recursion. What we basically do in this type of recursion is that we don't directly call the same function within itself. What we do is function f calls function g, and then function g calls function f. So indirectly function f is calling itself, and so that's why it's indirect recursion. The second example is that a function calls itself with a function as a parameter. So it's like the function is basically an argument for the function, for the recursive function when it basically goes through the recursive case. So in other words, it's like when you're calling recursion or calling the same function. So if you have recursive function f, for example, and you're trying to call it within call it again, then the argument of f would basically be again a function of f. And so in a way it's like nested. It's like just like we have nested for loops, we also have nested recursions where you use recursion as an argument of the function. Okay, so what is recurrence relation? A recurrence relation is an equation which defines the nth term in a sequence in terms of the previous terms in the sequence. So we'll basically be dealing with two types of recurrence relations for this class. The first one is t of n equals to a times t of n over b plus f of n, and the second one is t of n is equal to a times t of n minus b plus f of n. So basically over here a is basically the number of subproblems that the recursive function breaks the problem into, and then b dictates how much the problem is broken up after each recursive call. So for example over here, note that this is division whereas this is subtraction. So over here the problem becomes like n over b of the original problem, whereas over here it becomes n minus b of the original problem. So it's like smaller, but that basically dictates how much smaller the problem gets. And then f of n is basically the number of or the amount of operations done by the recursive function call. So once you are done with the recursive part over here, this is sort of like the base case, or not the base case, but like the part which basically combines the smaller subproblem to solve the bigger subproblem. Alright, let us look at an example of a function and then how do we make a recursive relation out of it. So okay, we have been given a function called 2 factorial what this basically does is that if you're given an integer, if n is less than or equal to 0, it will just return 1. Else it will return n times 2 factorial of n minus 2. Oh, okay, so basically it's similar to the factorial function, but if you're finding, for example, 10, the 2 factorial of 10, what you do is you do 10 times 2 factorial of 8, so 10 times 8 times 6 times 2 multiplied by 0, which I'm sorry, it's not multiplied by 0, it's multiplied by 2 factorial of 0, which would be 1. So basically the 2 factorial of 10 would come out to be the product of 10, 8, 6, 4 and 2. And then the 2 factorial of 9 would come out to be the product of 9, 7, 5, 3 and 1. Okay, so let us try to understand how we get the recurrence relation for this problem. So if you think about it, the number of subproblems that each recursive call creates is equal to 1, because you're basically having one recursive call, right? So it's like every problem basically breaks down into a problem which is like called just once, and then b is basically the amount by which the problem size shrinks for each recursive call. So in this case, so a problem of size n becomes a problem of size n minus 2, and then f of n. Okay, so f of n over here is basically n times this, which is n times the 2 factorial. So once we know the 2 factorial of n minus 2, it's just the product of these two numbers, right? So it's like big O of 1 because it's constant amount of operations. And so that's basically how we get t of n is equal to t of n minus 2 plus big O of 1. Alright, let us look at another example. So this is one of the examples from your quizzes. So we basically have an integer n, and if n is equal to 0, we'll return 0. Else we'll do basically the sum of the first n minus 1 integers, and then we'll add the sum of the first n by 3 integers. So basically what you're doing is we're breaking down the problem and then solving 9 of those problems. So what you're doing is basically a is the number of times the function will call itself in the recursive case. So this is basically a loop which gets called 9 times. So that's how we get a is equal to 9. And then by what factor does the original problem shrink? The answer is 3, because you're basically a problem of size n becomes a problem of size n by 3, and so it basically shrinks by a factor of 3. And then how many operations are performed during each recursive call? So obviously for every recursive call, we are basically using this for loop, which results in big O of n operations, because it's like getting looped over n times. And then this is again just constant because you're doing this 9 times. And so that's basically how we end up with f of n is equal to big O of n. And so when we combine all these three, we basically get t of n is equal to 9 times of t of n over 3 plus big O of n, and obviously the base case is when t of 0 is equal to 0. Alright, so once we get our recurrence relations, like how do we find the time complexities of the function, or like how do we basically solve those recurrence relations? So there are multiple ways of doing this. One of them is using master theorem, which is super easy once you know how to use it. And then there's tree method, which is easier when you have like multiple recursive calls in the same function, so something like binary recursion or something. So that's easier when you use tree method. And then there's iterative method, which is usually similar to tree method. It's just used more by like math-minded people. Okay, so what is the master's theorem? So basically, if you're given a recurrence of the form t of n is equal to a times t of n over b plus f of n. Okay, note that this is t of n divided by b and not n minus b. So in this case, basically, we can have three cases. We'll have a, b, and f of n, right? So one of the cases is when f of n is equal to big O of n to the log a base b minus epsilon. What this basically means is that um, n to the log a base b is basically asymptotically bigger than f of n. And so in this case, t of n would basically be big theta of n to the log a base b. If f of n is equal to big theta of n to the log a base b, then t of n would basically be equal to big theta of n to the log a base b times log n. And case 3 is basically when f of n is uh, asymptotically like greater than n to the log a base b. So in this case, we'll basically check one more condition, that if a times f of n over b plus is less than or equal to c times f of n for some c less than 1 and all sufficiently large n, then we'll say that t of n is equal to big theta of f of n. We can look into the examples for this, and that will make this more clear. Okay, let us look at an example of using case 1 of Master's theorem. So we're basically given a recurrence relation t of n equals to 9 times t of n over 3 plus big O of n. So if you compare this with the general equation, you get that a is equal to 9, b is equal to 3, and f of n is equal to n. And so that makes this case 1 because n to the log a base b. So if you do n to the log 9 base 2, you will get n squared because log 9 base 3 is 2, which is greater than f of n. So f of n is basically big O of n versus n to the log a base b, which is n squared. And so we'll basically use case 1, and we end up with t of n is equal to big theta of n log a base b, which is n to the log a base b, which is n squared. Alright, so here's an example of using Master's theorem case 2. So for example, we are given a recurrence relation t of n is equal to 2 times t of n over 2 plus n. Okay, first step, we basically extract a, b, and f of n. So we get a equals to 2, b equals to 2, and f of n is equal to n, right? Now we'll determine n to the log a base b, and so we get n to the log 2, log 2 base 2, which ends up being n again, right? And so now when you compare f of n with n to the log a base b, you get that both of them are basically asymptotically equal to each other, right? So we'll apply case 2, which says that t of n is equal to big theta of n to the log a base b times log n. So in our case, n to the log a base b is n, and then we multiply it with log n, so we get big O of n log n. Or we can also call this big theta of n log n, by the way. We'll just use the big O notation for this class, I guess. And so yeah, so that's that. Alright, so here we have an example of using Master's theorem case 3. For example, if you are given a recurrence relation t of n equals to 3 times t of n over 4 plus n log n. Alright, so in this case, our step 1 is again extract a, b, and f of n. So we get a is equal to 3, b equals to 4, and f of n is equals to n log n. And then we determine n to the log a base b, which is n to the log 3 base 4. And so we compare f of n with n to the log a base b, and we get that n log n is greater than n to the log 3 base 4. And so f of n is asymptotically larger than n to the log a base b, and so we'll basically apply case 3 over here. And we also need to check the regularity condition, which holds true in this case. And so we need some c such that a times f of, there's actually a typo over here, let me quickly change it. Actually, never mind. We substituted f of n is equals to n log n over here, and then we found f of n over b, which is a times n over b multiplied by log of n over b. And so this is less than or equal to c times f of n, where 0 is less than c is less than 1. And this condition basically holds true for c equals to 3/4 or any c greater than or equal to 3/4. And so basically we are also satisfying the second condition over here, which implies that the regularity condition is also satisfied. So we can say that this recurrence relation is basically its time complexity is big O of n log n. Alright, let us look at an example of iterative method and tree method. We can like look at an example, like we'll use both the methods on the same question. So for example, we are given t of n is equal to t of n minus 2 plus big O of 1, and the base case is when t of 0 is equal to 0. So if you think about it, this is, by the way, the iterative method. So t of n is equal to t of n minus 2 plus big O of 1. This is the first level, and then we break this down into t of n minus 4 plus big O of 1. And so now we know t of n minus 2 is equal to t of n minus 4 plus big O of 1, right? And so we'll basically substitute this over here, t of n, these whole value into this equation, and so we get t of n is equal to t of n minus 4 plus big O of 1 plus big O of 1, which gives you 2 times big O of 1, and this is the second level. And then similarly on the third level you'll get t of n is equal to t of n minus 6 plus 3 times big O of 1. And then on the kth level, in the general case, you'll basically get t of n is equal to t of n minus 2 times k plus k times big O of 1. And the base case is basically when t of 0 is equal to 0. So when t of n minus 2k is such that n minus 2k equals to 0, or in other words, n is equal to 2k, or k equals to n over 2, that's basically the case where we will stop like recursing. And so if you take your k pattern and substitute k in terms of n, you'll get that t of n is equals to t of n minus 2 times of n over 2 plus n over 2 times big O of 1. And so this ends up being t of 0, which is 0 from the base case, and big O of n. And so finally our answer comes out to be t of n is equal to big O of, or belongs to big O of n. And this is a more easier like visual representation of the same thing. Tree method is usually like more easier to understand because it's like more like for visual people, and it's easier to see the pattern. So when n is okay, so we have the big problem n, and then we break it down into n minus 2, and then we break it down into n minus 4, and then so on until we get the base condition, which is t of 0. And we get the base like 0 when k equals to n over 2, right? So basically the height of this tree comes out to be n over 2, and that's how we end up with the time complexity of big O of n. Alright, here are some sources I used for these slides, and I highly encourage you all to like use them if you would like to like prepare for the exam, or in general just to increase your knowledge. And good luck for your exams.